Have you ever looked at the spec sheet for a computer and just felt like you were reading a different language? Well, today we're going inside the machine. We're going to demystify the hardware that powers your digital life, translate those confusing numbers on a RAM stick, and even uncover the invisible security that protects you every single time you boot up.
Okay, let's just dive right in with a question you've probably asked yourself if you've ever shopped for a PC. You see that sticker on the RAM, and it proudly says 3200 megahertz. But is that really its clock speed? The real answer is, well, not exactly.
So to get to the bottom of this, we need to understand the difference between two key terms. On one hand, you have megatransfers per second, or MT/s. This is what marketers love to advertise because it's the bigger number, and it measures total throughput. But on the other hand, you have megahertz, or MHz, which is the actual speed of the clock. They're measuring two very different things.
And the reason for this mix-up is all thanks to this one brilliant piece of technology, double data rate, or DDR. It's in all modern RAM, and what it does is pretty amazing. It performs two data transfers for every single tick of the clock, one when the signal goes up and another when it comes down. Two transfers, one cycle.
And once you know that little trick, the math becomes incredibly simple. When you see a label like DDR4 3200, that means 3200 megatransfers per second. But since you get two of those for every clock cycle, you just divide by 2. And there it is. The actual clock speed is 1600 megahertz. It's the same deal for DDR5 6000. That's really running at a 3000 megahertz clock.
All right, so now that we've cracked the code on RAM, let's kind of zoom out and see how it fits into the bigger picture. The easiest way to think about your PC's performance is as a trio. You've got the brain, the workbench, and the filing cabinet.
First up, the brain of the whole operation, the CPU. Inside that CPU, you have physical cores. Think of them as the actual workers. A thread is basically a task that a worker is doing. The magic of modern CPUs is that they can make one physical core act like two virtual cores, letting one worker juggle two tasks at the exact same time. It's how your computer can do so many things at once without skipping a beat. Now, for that brain to work at lightning speed, it needs its own little stash of super fast memory right next to it. That's called cache. L1 cache is the absolute fastest and smallest, sitting right on the core for whatever it's working on right now. L2 is a little bigger, and then L3 is the largest cache that all the cores share. The whole point is to keep the CPU from ever having to wait for data from the much slower system RAM.
So if RAM and cache are the temporary workbench, let's talk about the permanent filing cabinet, your computer's long-term storage.
For a long time, this was the gold standard for fast storage, a SATA SSD. It was a massive leap from old spinning hard drives, topping out around 550 megabytes per second. But, as you're about to see, technology was just getting warmed up.
And what a leap it's been. I mean, just look at this chart. That SATA SSD is way down there at the bottom. But then you have NVMe drives, which plug directly into the super fast PCIe bus, and they just blow it out of the water. And the latest PCIe 5.0 drives, they can screen past 10,000 megabytes per second. The difference is absolutely incredible.
But you know, speed isn't everything. Reliability is what really counts. So if you remember just one thing about your drive's health, please make it this term, right here, reallocated sector count. And here's the crucial takeaway. If you ever use a utility to check your drive's health and you see this number go up, even by 1, that is a huge red flag. It means the drive is finding bad spots and scrambling to move your data off of them. It's failing. Seriously, back up your important stuff immediately.
Okay, we've covered the flashy performance parts. Now let's talk about the unsung hero of every single stable computer, the power supply unit, or PSU. This is where system stability really begins.
You've probably seen these 80+ ratings on power supplies. They've got different tiers, from bronze all the way up to titanium. And it's not just some marketing gimmick. It's a certified standard that measures how efficient they are.
So why should you care? Well, a more efficient power supply, say a gold or platinum one, wastes a lot less electricity by turning it into heat. That means a lower power bill for you, a cooler PC overall, and less heat stress on all your expensive components, which helps them last a whole lot longer. Speaking of reliability, it's not just about the power. In the world of servers and critical workstations, they use a special type of RAM called ECC. That stands for error correcting code.
Unlike the RAM in your PC, it has an extra chip that can actually detect and fix memory errors on the fly. For those systems, ultimate stability is way more important than raw speed.
All right, for our last topic, let's talk security. We're going to look at this invisible process that protects your PC in that very first second after you hit the power button before you even see a logo on the screen. For decades, PCs used something called a BIOS to get started. It worked, but it was slow, had huge limitations, like it couldn't handle drives bigger than 2 terabytes. Its modern replacement, UEFI, is way faster, supports massive drives, and most importantly, it enables some critical security features.
And the biggest of those features is called Secure Boot. It works like a digital chain of trust. When your computer starts, the UEFI firmware checks the bootloader. Then the bootloader checks the operating system. Each step validates the digital signature of the next one. This makes it pretty much impossible for nasty malware like a rootkit to load up before your antivirus even has a chance to start.
The hardware anchor for all of this modern security is the Trusted Platform Module, or TPM. Think of it as a tiny, tamper-resistant safe built right onto your motherboard. It securely stores all the cryptographic keys and measurements that your system needs for features like full disk encryption or secure logins. It's the physical root of trust for your entire PC.
So, as we wrap things up here, it's pretty clear that a modern computer isn't just a collection of parts in a box. It's a whole interconnected system. You've got to have those high-performance components, like the CPU and SSD, but they're useless without the stability you get from a good power supply. And all of it has to be protected by a secure foundation built on UEFI and the TPM.
And that really brings us to the end. So I'll just leave you with this one question to think about. After peeling back all these layers, what's the one component, whether it's your RAM, your power supply, or that little TPM chip, that you'll think about differently the next time you power on your machine?